Hi, everybody. Welcome back to Dave's Math channel. This is my next feature on the Math Lovers book. I'm up to section 2.3 on greatest common divisor. I made another video yesterday on what the GCD is. Greatest common divisor, also known as GCD. And I also presented a kind of a straightforward algorithm for computing it. But today I'm going to talk about another algorithm for computing the GCD. As a matter of fact, it's a more efficient algorithm, and I think it's even an older algorithm. It's known as the Euclidean algorithm. It's still the most efficient algorithm we know for calculating greatest common divisor of two integers. So anyway, let's begin. So anyway, what is the Euclidean algorithm? Well, it's I wrote it down on the bottom of this slide. It's a very old algorithm. I mean, it was developed by Euclid, like the name says, very famous ancient Greek mathematician, the same Euclid who came up with Euclidean geometry. We don't know very many details about his real life, but we do know that he was an amazing mathematician. Not only did he come up with Euclidean geometry, and also he came up with a proof that there were infinitely many prime numbers, and came up. I think he also proved the fundamental theorem of arithmetic, which says that every integer has unique prime factorization. So he did a lot of amazing work. Not only that, but he came up with this algorithm called the Euclidean algorithm for factoring. I mean, for computing the greatest common divisor of two positive integers. And so here it is written out. And maybe it's better to just go over some examples instead of going over this algorithm, because this might not make much sense to you. So I think I'll just do some examples. And I have another video I made about the Euclidean algorithm. You might want to watch that one as well. But I think I'm just going to present some examples. And then I think once you see a few examples, you'll see how this algorithm works. So suppose we want to calculate the GCD, use the Euclidean algorithm to calculate the GCD of 12 and 18. And it's customary to write I wrote this in the wrong order because it's customary to start with a larger number. So what you do is you call R0 18 and R1 12. That's how you start this thing. I might as well show you the algorithm again. So R0 is you're trying to calculate the GCD of A and B. And by convention, we let A be the larger number and B be the smaller. If they're equal, then the GCD is just each of the numbers. So there's really no work to do in that case. But usually they're different, and in that case, we just let the R0 be the larger number, R1 be the smaller number. So in this case, R0 is 18 and R1 is 12. And then what we do after that? Well, then we record this recursive procedure. This is what's called a recursive algorithm. So we go through a loop, and this index k is just indicating that's how many times you have to go through the loop. So you start with k equals 0, and then you check whether your last rk plus 1 is 0 or not. It's not in this case because our r1 is 12, so we have work to do still. So the next thing we do, r2 is going to be the remainder when we divide 18 by 12. So when you divide two numbers, in general, the second number doesn't divide evenly into the first number. When it doesn't, you get what's called a remainder. I'm sure you guys all know about this quotient and remainder. So when you divide 18 by 12, we don't care about the quotient in this case. The quotient is 1, but we don't really need to know that. The remainder is 6. When you divide 18 by 12, you get 1 with a remainder of 6. In other words, 18 divided by 12 is 1 and 6/12. So our first remainder is 6, and that's going to become our next value of r. Our r2 is going to be 6. It might have helped if I drew a table here. I didn't do it in the book, but so now we keep going. So now our r1 was 12, and our r2 was 6, and then we apply another step of this algorithm. And again, not this time we're gonna divide 12 by 6, and in this case 12 divides evenly by 6. You get a quotient of 2 and a remainder of 0. So now, since you have no remainder left, that means the last non-zero value of r that we had, namely 6, r2 equals 6, that's the GCD. So that's how you compute the GCD. You just keep computing remainders recursively until you can't do it anymore. and the last remainder is your answer. Let's do a little bit harder example. Example 2. How about the GCD of 42 and 77? Once again, you want to write the larger number first. So we start with 77. That's our R0. Our R1 is 42. And the first thing we do is divide 77 by 42. That's going to give you a quotient of 1 and a remainder of 35. You can check that. So our R2 is going to be 35. And then we do the next recursion. We divide 42 by 35. And once again, we get a quotient of 1, but this time we get a remainder of 7. So then we have one more step. So we try dividing 35 by 7. And 7 divides evenly into 35. 35 divided by 7 is 5. This time the remainder is 0. So we're done. The last non-zero remainder we had was 7, and that's the GCD. Therefore, the GCD of 42 and 77 is 7. Pretty simple. And the nice thing about the Euclidean algorithm, it works for as large numbers as you want. It's a very efficient algorithm. I mean, if you started with some big, humongous numbers, remember the method I went over yesterday where you were calculating the prime factorizations of the number you're starting? That is another way to do it. But that's not an efficient way to do it. Imagine you start with some huge numbers with some huge prime factors. It might take forever to factor those numbers. But you don't have to know how to factor them. All you have to know how to do is apply this Euclidean algorithm, and it always works very quickly, no matter what numbers you start with. That's the beauty of the Euclidean algorithm. And there's just one more thing I want to talk about. So you can do this with more than two numbers, too. And I give a couple examples where I use, first example, I give three numbers. So suppose we wanted to calculate the GCD of 18, 30, and 45. This is a little hard to read. I didn't copy too well. But in that case, you can only calculate GCDs one at a time or two at a time. It's kind of like addition or multiplication. You can only add two numbers at a time. You can add as many numbers as you want, but you always have to do them two at a time, and then you just you add the third number after you've added the first two. It's kind of the same thing with the GCD. So if you're given more than two numbers you want to compute the GCD of, I guess the algorithm I talked about yesterday, you could use it for as many numbers as you want it. But for the Euclidean algorithm, you can only use the Euclidean algorithm on two numbers at a time. So if you want to use the Euclidean algorithm to compute the GCD of three numbers, say 18, 30, and 45, you'd have to first start with one pair. And I started on the left. It might have been better to start on the right. It's usually better to start with the bigger numbers first. It's kind of a mistake I made in this book. But I'll just go over it the way I presented it here. So we could do the GCD of 18 and 30 first. And I'm not going to go through all the steps. You can do the steps yourself. And you'll find that the GCD of 18 and 30 is 6. So now we're left with the GCD of 6 and 45. And I might as well go through the steps with that one. It's not too hard. So you divide 45 by 6, and that gives you a quotient of 7 and a remainder of 3. And then you divide 6 by 3. That gives you a quotient of 2 and a remainder of 0. So the last non-zero remainder you had was 3. So therefore, the GCD of 18, 30, and 45 is 3. Pretty simple. And I have one more example below that one. Oh, no, actually, I don't. But then I do an example involving four numbers, and it's the same idea. I mean, so let's just go over this one. I think I will do this in reverse order, actually. I kind of did it in the wrong order on this slide. But suppose we want to compute the GCD of 60, 90, 140, and 175. Well, let's start with 140 and 175 because I think that's a better way to do it. So if again, you always start with a larger number first. So you take the GCD of 175 and 140, and you just divide 175 by 140. That gives you 1, quotient of 1, remainder of 35. Then you divide 140 by 35. That gives you a quotient of 4 and a remainder of 0. Therefore, the first GCD is going to be 35. So now we have the GCD of 90, 60, and 35. And again, it's usually a good idea to start with the biggest ones first. So let's do 90 and 60 first. So the GCD of 90 and 60, well, you 90 divided by 60 gives you a quotient of 1. and a remainder of 30, and then 60 divided by 30 gives you a quotient of 2 and a remainder of 0. Therefore, the GCD of 90 and 60 is 30. So now we're left with just a GCD of 30 and 35, or 35 and 30 if you like. And again, it's pretty easy at this point. 35 divided by 30 gives you a quotient of 1 and a remainder of 5. And then you do 30 divided by 5, that gives you a quotient of 6 and a remainder of 0. So 5 was the last GCD, and that's what, now we're done. The GCD of these four numbers is 5. So that's how you do that. It's a very efficient algorithm, and you can use it on as many numbers as you want. It's pretty beautiful. So that's GCD. That's the Euclidean algorithm for computing the GCD of as many numbers as you like. And that completes my video for tonight. So thank you for watching. Long live math, and I'll see you guys next time.